Hello and welcome to the course on AI ML in Materials Engineering. I am Professor Tarun Kumar Kundu from Department of Metallurgical and Materials Engineering, IIT Kharagpur. So on request of Professor Biswas, I will be taking two lectures on molecular dynamics and density functional theory based methods. Okay. So these two methods have got importance in materials science, computational material science, and also designing of new materials, even to get the estimation of the properties which we cannot get it from the laboratory setup. Okay. So AI ML are used to get some of the parameters for running density functional theory calculation and also molecular dynamics calculation. At the same time, the information we get from, let's say, DFT based calculation or molecular dynamics calculation, that can be used as a database to further use this AI ML method. So this is a kind of a two-way process. Both these molecular dynamics and DFT based simulation add to the database. At the same time, also AI ML also help in getting better potential for DFT method, or even to get the better functional potential for molecular dynamics method, or functional for DFT based method. Okay. So its time is very short, so I will be covering only the main principle behind the molecular dynamics simulation and density functional theory based simulation. So in the first lecture, I will be covering the basic principle behind the molecular dynamics method, so that you get the background theory. At the same time, also when you use AI ML methods to get the parameters for MD run, so you get to know where it is used and how it is been used. So today I will be covering, basically introduce with the computational material science, different methods suitable for different system size, because a single method you cannot use for different size of the system. Some of the methods are useful for very low scale system, or even some of the methods are useful for a kind of the engineering design method or a component of a machine and all. Okay. So I will be covering also the four paradigm of science, where empirical, theoretical, computational, and data driven. So that's give you the connection between the computational and data driven. That means the computational, in this case we can say that the molecular dynamics or the DFT with the machine learning methods. Okay. So I will be covering mainly molecular dynamics, which is essentially a Newtonian mechanics method, but DFT and the ab initio method are essentially we use the quantum chemical methods. Okay. And also we will see how the atoms are modeled in the molecular dynamics method. So we will be covering the methods, application, and limitation of molecular dynamics, and interatomic potential for molecular dynamics, different algorithm used to solve this Newtonian equation of motion in the molecular dynamics methods. We will be covering mainly three mostly used algorithms, and also we will see what are the procedures followed for doing a molecular dynamics calculation. Essentially, some of the pre-setups, initialization, equilibration, production runs, data generation, and property calculation. At the same time, also if time permits, we will see that what are the criteria you need to see whether the runs are valid, the MD runs are valid or not. Okay. So these are the keywords which we can search, and also these keywords are essentially described in these lectures. Okay. So coming to the position of molecular dynamics in the overall setup for materials, computational materials and materials design, as you know that some of the process we can use for very short size, maybe in the range of, let's say, few angstrom, maybe in the range of nanometer range, we have to use the quantum mechanics method, which is called the electron structure method or ab initio methods. And under these ab initio methods are the Hartree-Fock method and density functional theory based methods are used. Hartree-Fock methods, essentially we solve the Schrodinger equation with some of the approximation. In the case of density functional theory, where instead of wave function we use the electron density and use the quantum equations, but the Hartree-Fock principles are also have the lineage with the DFT. So in the next class, when we discuss about the DFT method, also we'll first discuss the Hartree-Fock method, and then we'll move to density functional theory method. Okay. So this electronic method or the ab initio method, we can use only maybe less than 1000 atoms. Okay. Then we move to molecular dynamics, which is the main topic for today's lecture. Essentially, we can go to little bit larger size, maybe 10 to the power 10 number of atoms, where essentially we solve the Newtonian law of motion, like force equals to mass into accelerations, and which is essentially called the atomic scale. So in this case, we cannot deal with the electronic property. Okay, so because we don't consider electrons, we consider atoms as a kind of a sphere or deformable sphere, and then we use the Newtonian mechanics. Okay. So now if you have to go to a little bit larger size scale, essentially we need to use some of the statistical based methods. Essentially these are called or mesoscale method or microscale method, where we can use the Monte Carlo simulation, and we can use the Metropolis Monte Carlo simulation to simulate the thermodynamic ensemble, or we can use the kinetic Monte Carlo simulation to simulate activated process like diffusion and all. And for the larger size system, essentially we need to go for the finite elemental methods, where we divide the system into small elements and calculate the variables like stress, strain, pressure, temperature as a set of algebraic differential equation and or integral equation, and solve by some of the numerical methods. So in this case, we can simulate some of the deformation behavior, or we can simulate the convective transfer of heat and mass and momentum also. And later on, we can get also the engineering design. So essentially, it's give you the overall range of the scale and also different method we can use. So in all the cases, essentially the three basic among the four basic force, which is the mainly force, we consider only the electromagnetic interactions. Okay, of among the nucleus and electrons and atom. Sometimes the system size may be little bit larger, but at the same time also we need to look at how a small portion reacts. In that case, we need to combine two methods like quantum mechanics and molecular mechanics, which is called the multi-scale method, or it's called QM-MM method. Similarly, also some of the parameter we can get from the molecular dynamics, and those we can use and some of the phenomenological methods, or even in the finite element methods. So which is essentially are the which are essentially the multi-scale method. Okay. So this gives you the overall spectrum of different methods and where we can use, and the position of molecular dynamics and DFT in the overall spectrum of the calculation methods. So this gives you the different length and time scale for in material science. Here we can see that for the atomic range, essentially in the range of 10 to the power minus 9 millimeter, and the time scale in 10 to the power minus 12 seconds, we need to use the molecular dynamics, or you can. And for the case of the electronic structure based property, essentially they range in the range of 10 to the power minus 11 meter, and the time scale is also very short in the range of femtosecond. In that case, we have to use the quantum mechanics. Okay. So as we go down, we need to go to the quantum mechanics or wave mechanics based method. At the same time, also it also takes more time to solve it, and which also dictates the number of atoms or number of constituent we can deal with. Like Schrodinger case, in exactions it can be solved only for one particle system or one electron system. But if we do some of the approximation, like in the case of the Hartree-Fock methods, we can go up to, let's say, 50 or 100 atoms, and the scaling in the range of n to the power 4, where n is the number of atom. Okay. DFT scale, we can go to little bit larger size, maybe in the range of 1000 atoms, and the scale generally is range from to n to the power cube. Okay. Molecular dynamics, essentially it's a kind of a linear scaling with respect to the number of atoms we deal with. Okay. So essentially each approach represent a different balance among computational efficiency, tractable system size, accuracy and predictive power. So essentially, as you go to the DFT method or Hartree-Fock method, these are more precise compared to, let's say, molecular dynamics. Likewise, for material science, we have to go for molecular dynamics method or DFT method on the based on the maximum number of atoms that can be handled. Okay. So now first principles methods are becoming popular day by day, but molecular dynamics still serves where the quantum effects are negligible. That means where we don't have to deal with the electron transfer or electronic interaction. But quantum effects become significant only when the particle wavelength lambda is compatible with the interatomic distance, where maybe in the range of, let's say, in angstrom. Otherwise, the use of easier Newtonian equation motion is well justified. Okay, so this gives you the perspective on the molecular dynamics methods. Okay, so for paradigm of science, because this main course is on the AI ML, and where does it connect with the molecular dynamics and DFT method. So essentially first paradigm, that means the earlier time, essentially it was kind of the empirical science or experimental based observation, and then also the manipulation of the observations, and also some of the getting some of the empirical way. Then comes the model based theoretical system, like in the case of, let's say, laws of thermodynamics and all. But as the time progressed, the analytical solution of this the law based system became difficult. By then essentially we need to, when at the advent of computers, essentially we go for the computational science, essentially DFT based methods and molecular dynamics methods. So essentially this is in the third paradigm, okay, which is today's lecture. But the fourth paradigm comes when it is of the big data driven science, where you have got predictive analysis, clustering relationship, data mining, anomaly detection and all. So this now essentially this data driven science require data. Where from we get the data? We get the data from the experiment, or we can get the data from the third paradigm or computational science. So essentially there is a direct linkage between this computational science or this DFT or MD simulation with the AI ML. At the same time, some of the parameters required for running DFT or to run MD also we can get by using the get or refine it further by using the data driven science or molecular. So essentially this is a two-way process. Both of them are contributing and progressing at the same time. So now coming back to the main molecular dynamics methods, we need to discuss about the main concept behind it. Essentially, we consider the system is made up of atoms, but in the case of the atoms, essentially we know that it is made of nucleus and electrons. But in the case of the molecular dynamics, we omit this electron part and we just club it together as a atoms. Okay, but this essentially we give the mass at the center of it. So essentially we consider as a point mass. At the same time also we may give some of the charge. Okay. So in MD, an atom is basically approximated as a sphere with point mass, and electron role is totally neglected at the same. If we neglect the electronic mass, essentially electronic based property we cannot get from the molecular dynamics. That means we don't get the reactivity, or let's say we cannot get band gaps and all these things. Okay. So essentially, let's say we atoms. Now how this atom behaves in presence of others and under the influence of different external parameter like external temperature, force, even stress, even electric field and all. Okay. So essentially those field will give the force to the atoms, and this atom will move. As it moves, also it will get different position and also momentum, and we can utilize those this velocity, position and all, at the same time also the overall energy to get some of the thermodynamic property or some of the other process related properties. Okay. So a typical procedure of MD, so in this case let's say number 1 atom, so move from dotted to the solid wall position. So essentially let's say it was initially at the dotted position, then it's moved to this due to the force imparted by the nearby atoms. And of course we need to use this step, that means how much it is moved in a small step. We need to use the time step, and this time step has to be such that within this time step no such significant process takes place. That means it has to be less than the sum of the whatever the process, the high frequency process takes place. So it gives essentially it is as the F equal to ma dictates. So essentially we need to get the force, and this force we get it from the potential under which all the atoms are. So we take the negative gradients of the force field, to get the force. From the force we can calculate the acceleration, and with this acceleration using this acceleration we can get the new position or new velocity. That is essentially the basic principle behind the molecular dynamics. Okay, basic principle is the force calculation and how the atoms move under this force. And now you need to deal with, let's say, thousands, even millions of atoms. So you need to calculate the force on each atom, at the same time also how it moves, its new position, how the velocity changes and all. And at the same time also we need to see how it changes with respect to temperature, external temperature, pressure and all. At the same time also we need to see the most of the cases we need to see the molecular dynamics is done at under constant energy. So if it's constant energy, that means essentially kinetic energy and potential energy are constant. So there will be this distribution. Okay. So in order to get different properties, we need to use different conditions, and these conditions are called ensembles. Okay, we'll see what are the different ensembles are used, what are the different algorithms are used to see under the force how the particles moves. At the same time also we need to see how we can converge it under the different constraint, like that constant temperature, constant pressure, constant energy and all. Okay. So coming back to the main methods, molecular dynamics is an integration of Newton's equation of motion over time to obtain the time evolution of the atoms and thus the properties of our interest. Given the initial position and velocities of every atoms and using the provided interatomic potential, the force on each atoms are calculated. We will see what are the different interatomic potentials are there. Potential is essentially the field. As a particle moves under the gravitational force, particles moves. Similar way also the atoms in molecular dynamics essentially moves due to the potential field, we can say, or potential under the potential energy, and this potential energy are given as a kind of the sum of the analytical forms and all. So which are parametrics, and these so AI/MLs are mainly useful to get these parameters. Okay, most of the cases we get the parameter from the experimental observation, or we get the molecular dynamics parameter also we can get it from the ab initio calculation also. So using this information, essentially information means this if you have the initial position and the velocity of every atoms, and using the potential we can get the force. So using this force and the velocity, the initial position are advanced towards the lower energy state through a small steps, okay, which is called the time step, and which results in new position, new velocity and so on. Okay, so with the new data as inputs, these steps are repeated maybe more than 1,000, maybe million times also, until an equilibrium is reached and the system properties do not change with time. That means we need to first equilibrate it and then also run the system, run the molecular dynamics. So during and after the equilibration, various data like atomic position, momentum, energy, force are stored for each or some time interval, which can be used to calculate different properties. So these are the main use of molecular dynamics. We can get the property like energies, structural and mechanical property, expansion or diffusion coefficient, melting point, heat capacity, thermal conductivity, free energy, phase diagram, and also we can get the structural property like the radial distribution function directly or via the statistical analysis. Okay, so these time dependent properties we can collected it, and then we can use the statistical methods, which is called the ergodesic principle. If it's satisfied, then we can get all this property using the statistical analysis. So what are the other application of molecular dynamics? We can also get the description for processes and phenomena such as sputtering, vapor deposition, fast plastic flow, crack growth, and fast structure, nano indentation, propagation of shock wave, detonation, irradiation, ion bombardment, cluster impact, and operation of the nanogear. So these are the few application, but this is not the limited. Okay, so the applications are growing day by day, and people are using anywhere where the experimental setup are not possible due to either very high temperature requirement or maybe very hazardous atmosphere and all. Okay, and at the same time also, before we go for any experiment, also people can go for first see how the materials behave. First we go for computational methods to see how the materials behave, and then we go for, so that we can tune number of experiment we need to do and all. Okay, So some of the limitation of molecular dynamics: compared with the first principle method, molecular dynamics is extremely fast and can handle much bigger system, which is good news. However, some of the limitation of molecular dynamics include availability of potential is limited, especially for multi-component system, and the accuracy of a potential is always under questions. And length scale is still not macroscopic. So maybe in the range of some nanometer, but it is not in the macroscopic range, and time scale is also limited to nanosecond. Okay, so even going to microseconds is also very difficult and time consuming. Okay. So no electromagnetic properties we can obtain, no electronic property, no electromagnetic property, magnetic property we can get using the molecular dynamics methods. Okay. So main thing in molecular dynamics is the force exerted on the atom due to the field, and this field is represented by the interatomic potential. Okay. So we need to discuss more on the interatomic potential. So when atoms are near enough to feel each other, the balance between attraction and repulsion takes place, and it is determined by interatomic potential, or this potential are essentially sum of the attraction and repulsion force between the atoms. Okay. So atoms can eventually settle down at a minimum potential state at the equilibrium distance following Newton's equation of motion, and the sum of all the force acting on the atom we can just use F equal to ma, and A also you can write it as dV dt or d2r dt square, or as a kind of the rate of change of the momentum. Okay. So if the total energy is constant in time, which is the case for an isolated system, for MD simulation, force is related to the negative gradient of the potential. Okay. So with respect to the position, that means if you know the potential, then if you do the gradients, or that means the differential with respect to the position, and take the negative sign out, we can get the force. So if you know the force essentially, and we know the mass, so essentially we get the acceleration. Okay. So if you know the acceleration, from there we can calculate the velocity and momentum and all. Okay. So therefore, if we know the potential of a system as a function of interatomic distance, then we can have the forces on atom, and thus can solve this equation for time evolution of the system. Okay. So potential for specific system are generated by fitting some certain function with parameters of experimental data, like some of the experimental data which is used to get these potentials are essentially potential are not but is the some of the mathematical functions. Okay. So this function can be polynomials. Nowadays polynomial functions are mostly used for to get the parameter by using AI and ML method. Okay. And other cases also some of the empirical the relationships also we can use. So what are the experimental data we can use to fit this potential fit the parameter, or to get the potential interatomic potentials are equilibrium lattice parameters, cohesive energy, bulk modulus, elastic modulus, vacancy formation energy, thermal expansion coefficient, dielectric constant, vibration system, and also surface energy, or it can be calculated from the first principle methods. Okay. So these empirical potential are system specific. One should ensure that this is transferable. Transferable means, let's say we get the potential for some, let's say two interacting atoms in one environment, that same potential may not be used. Those two, the interaction between two atoms if the surrounding atmosphere is different. Okay. So this transferability is very important for getting the empirical potential. Okay. And it should be careful about using one specific potential for other systems or conditions. Okay. So even under the same system and condition, some potential may result in different dynamics. In most of the potential are usually constructed by fitting to static properties. Okay. Significant progress has been made in recent years in generating accurate and reliable potential for many metallic systems, semiconductor, and some of the other dynamics methods. So ML AI are being increasingly used to generate the interactive potential. So here is the main use of AI ML in molecular dynamics. Okay. So we will discuss a few important types of interatomic potentials. Okay. But this is not the limited. People can use nowadays new types of potential people are using. Okay. So some of the most used potential are the fair potential. Essentially, this is nothing but the Lennard-Jones type of potential depicting the van der Waals type of forces. Okay. So in this So if you have n atom systems, an atom I interact with two atoms. So essentially pair atom means we are considering the interaction between two atoms only. Okay, but overall interaction can be between two atoms, or which we call pair, or if the two atoms are bonded also we can call it as a bonded interaction. Okay, or it can be interaction between three atoms, which we call triplet or angular. So either it can be, let's say, three atoms are not bonded, or it can be bonded. So if the three atoms are bonded, essentially it form an angle. Okay, so we call it angular angular potential. Okay, or what's one, or we call it the bond this bending potential. Okay, and it can be four atom system. So essentially if these four we call it quartet, or it can be dihedral. So if the four atoms are bonded, so essentially what changes is the dihedral angle between them. Okay, and so forth, and anyone. But in this case we are considering only pair potential, then that means the interaction between two atoms only. So you can, so this is the overall potential, and we are considering only this first term for the pair potential. Okay, so considering only the two atom pair interaction, neglecting all others, there are n minus 1 interaction per atom, and thus the number of pairs will be in order of the n square. So number of pair will be n into n minus 1 by 2. So it will be in the order of n square. So if you have, let's say you have five atoms, so the number of pair interaction, all these these arrows gives you essentially 10. Okay, but it is, though it's for a small number, it is for 5 atom it is 10, but essentially if you go larger, so essentially it will ultimately come down to the as a order of n square. Okay, so how we generally dictate? So if it's bonded, essentially we do it as a kind of a bond stretching model. Okay, but if it's not bonded, sometimes also the bonded also, it is bonded, at the same time also it can have certain kind of this Van der Waals interaction. In that case we need to add both of this. Okay, so if there is no bonding interaction, so essentially we can, like in the case of the let's say noble gas, or if we have very hard spherical molecules and all, so in that case we can use this Lennard-Jones types of potential, which is expressed in terms of the interatomic distance. Like this potential looks something like this, where energy is in the y-axis and the separation distance in the x-axis, and it say that it will have a corresponding position at which the energy is minimum. At the same time also it will have the distance at which the energy is 0. So we consider this energy well, or this epsilon, and also the separation distance where the potential is 0. So these two parameters we can use to get the estimation of the repulsive potential and attractive potential. Okay, so attractive potential generally little bit in the larger size, and if it moves to very close cases, essentially you have the nuclear repulsion type. Okay, so this is the Lennard-Jones potential, very famous, 4 epsilon sigma by r to the power 12 minus sigma by r to the power 6, and from there we just, as we mentioned, that the negative gradients will give you the force. So the force will be 24 epsilon by sigma 2 sigma by r whole to the power 13 minus sigma by r whole to the power of 7. So this is essentially the Lennard-Jones potential, which is used for noble gas. At the same time also, when you have got bonded molecules like hydrocarbons and all, there also essentially we use the bond stretching model. At the same time also we can add this Lennard-Jones potential in order to give some of the Van der Waals types of interaction also. So the pair potential may not be used, we cannot use it for metals, where which have got the metallic type of bonding. So in that case essentially we go for this embedded atom method, or EAM potential. So in atoms or ions are in the middle of the electron C, and mostly coordinated with, because number of the atoms with which a particular atom is kind of the close or coordinated are quite high, maybe in the range of 8 to 12. Okay, and the Coulomb interaction between them are long range one. Long range means essentially not only the nearest neighbor. So the long distance neighbors also have got the interaction. So that's how it is called the long range order. Okay, and this long range order may be covering easily 10 to 20 atoms. Okay, so the embedded atom method consider the effective electron density at a given atomic site as one of the parameters, thereby capturing some of the electronic effect while maintaining the simplicity of the potential. Okay, Essentially in metal, valence electrons are delocalized as an electron clouds like here, okay, and exhibit an additional attraction towards this atom. So, whatever this the delocalized electrons also have got the attraction with the ionic core, okay. And this AM potential consider both the contribution from the positive or repulsive pair potential and also the negative or attractive embedding energy, okay. So, energy that is required, embedding energy nothing but the energy that is required to embed positively charged atom core into an electron cloud density that approximate the missing n atom effect in a pair potential. Essentially the electronic or EM potential, you have this the pair potential, at the same time also you have got this embedded potential given as a kind of the as a function of this charge density. Essentially this charge density, again we need to rely with the DFT based calculation. So, fitting this AM potential is also time consuming, and if you have different setups, let us say different alloys and all, so it also take times to get this EM potential, okay. So, some of the ready-made potential are there for some of the selected systems like say copper, aluminum and all, okay. So, in the case of the EM potential, essentially the second term is the embedding energy function as a, and Rij is the scalar distance between the two atoms I and J, and this first term or the pair potential, again it is given as the interaction between the different atoms, okay. So, 1 2 1 3 like this, okay. And this rho I, so essentially this is the charge density at a particular core, again it is given by it is affected by some of the other charge also, or the other atomic charge or core charge, which is given by Pi equals to half of the summation of Pj Rij, where J not equal to I. Now comes to the Tersoff potential. So, these Tersoff potential are basically we can use for covalent solids, okay. And in covalent solids, so deviation from the scheme of pairwise additives are even larger, since these solids are less closely packed, open with a coordination number of only 4 and have strong directional bonds of equivalent strength, okay. So, bond angle and bond order are the prime characteristics of these materials, and the strength of a bond between two atoms depend on the local environment such as the coordination number and also the bond angle. So, somewhere we need to use this coordination number, okay. So, Tersoff recognize this geometrical fact and develop a potential in this form, okay. So, essentially Tersoff potential is the summation of this the repulsive force and also the attractive force, okay. But in the case of the attractive force, essentially we scale it down using this bond order Bij, okay. So, this Bij is the bond order for bond between atom I and J, and which is normally a decreasing function of the coordination number. So, this Bij take care of the coordination number, and this Bij is essentially inversely proportional to the square root of the number of the coordination number, okay. Although both this term depends upon the distance, because you can see that first term and second term, attractive term and repulsive term depends upon the distance, and this type of potential usually has more than 6 parameters to be fitted. With a good parameterization, this potential have worked well for where you have got some of the covalent type of characteristics like silicon carbide, semiconductor like silicon, diamond, amorphous carbon, some of the hydrocarbons and all. Then interatomic potentials for ionic solids, essentially where they more than the covalent force is very less compared to the ionic force or coulombic type of force. So, in that case we need to use this potential. Essentially we call it Buckingham potential, okay. So, in ionic solid, ions can be polarized or charged, and the coulombic components can spread into a very long range, and it generally predominates, okay. And to describe potential for this solid, one must consider two pair interaction terms, short range term, at the same time also the long range potential. So, essentially the ionic charge essentially have the short range, okay. It can be pair potential, or it can be and also the long range one, okay. So, long range is essentially nothing but the coulombic potential, coulombic force, okay, coulombic potential. And the short range, essentially we write it in this form. So, not exactly the Lennardt's potential essentially, but we use this form C1 exponential of minus Rij by rho minus C2 by Rij square, where rho, C1 and C2 are the constant. We need to again fit these parameters, okay. Z1, Z2 are charges of these constituting atoms. Rho, C1, C2 are the constant in the short range Buckingham potential. So this is the Buckingham potential. So overall ionic potential will be Buckingham potential plus the Coulombic potential. Okay. This Coulombic interaction term is the long range type that decays, that as you can see it is 1 by Rij. So for an ionic crystal, this term under periodic boundary condition, we will see what is the periodic boundary condition and why you need to use the periodic boundary condition for molecular dynamics simulation. So this periodic condition cannot be treated with the usual energy cutoff approach because the potential periodically accumulates and imposes serious divergent problem. So instead of energy minimization, energy will increase if we treat this 1 by R basis, this Coulombic potential. But we can effectively deal this case that essentially instead of diverging it should go to converging. Okay, so essentially for that we use the yield sum techniques which generates an artificial charge distribution localized around each of the ion twice. Okay, so essentially we use some kind of the cancellation process, or we need to make this long range force into a short range force. Okay, so we need to use some of the reciprocal phase and also distribution of the point charge into Gaussian kind of distribution and all. Okay. So I am not going very details of this yield sum technique, but essentially the thing is that we need to make it short range, and in order to make it short range, essentially we need to go for use for the Fourier transformation based method in the reciprocal phase. Okay, so in that case, at the same time also we need to spread out the charge from point charge to the kind of a Gaussian kind of distribution. Okay, so how we neutralize it? Essentially, how you use this? First, with the opposite sign, essentially which cancel the original charge, thus behaves as a short range, and next with the same sign as the ions expressed in a spherically symmetric Gaussian type and treated by first Fourier transformation in reciprocal phases. Now some of the cases in ionic solids, some of the anions, mostly the anions are maybe also it can deform under the influence of the other atoms. So you need to have the avenue to change its charge its ionic charge under different condition. Okay, so in that case we use the cell potential to represent this highly polarizable anions. Now all this potential what we have discussed is a kind of atomic base. We cannot deal with the whatever the electron transfer or electronic interaction, but people also try whether we can get the some of the flavor of the DFT or ab initio method in molecular dynamics itself by tweaking the potential, and which is called the reactive force field potential. Okay, so this is also very widely studied subject nowadays, and this is the reactive force potential field development is also on a big work is going on under AIML methods also. So reactive force methods potential made of tens of parameters that are determined by first principle calculation, and these potential are designated to respond dynamically to the local environment and to describe some of the bond forming or bond breaking in situ. So bond forming and bond breaking is nothing but the electronic transfer method. Okay, although they are roughly 10 times slower than the earlier mentioned potential, and their successful application for hydrocarbons, nanotubes, the semiconductor system have made the approach very popular and promising. At the same time also it is promising for applying the AIML method also. So after discussing on the potential, now we need to see how this potential dictates the how we get the force from this potential, and how this force also dictates how much the particles move. Okay, how the displacement of the displacement of the atom. Okay, so we need to use some of the algorithm or the procedure to solve the Newton's law of motion. Essentially, Newton's law of motion is a differential equation. Okay, so for differential equation, essentially the solution is the integration or analytical solution. But analytical solution of let's say thousands or let's say millions of atoms is very difficult. So we need to resort to the numerical methods. So that's why we need to go for numerical algorithm. Okay, so the total force of an n-atom system. So n-atom we can represent with for each atom we can represent with x, y, z or the space coordinate. At the same time also we can represent with the momentum coordinate also in phase space. Okay, so so it will have 3 n atomic coordinates system with the empirical potential. Newton equation of motion can relate force to the derivative of the potential energy to the change in the position as a function of the time. So essentially force is nothing but summation of mass into acceleration. Acceleration also you can write it as d2r dt square, okay, and this force is nothing but the negative gradients of the potential. So, U is the potential and this potential can be different types of potential as we have discussed, okay. In principle, the first and second integration of the equation will result in the velocities, okay, and the position. That means dr dt will give you the velocity and all, okay. So, however, analytical solution, because what we are getting this the A, okay, and A is nothing but d2r dt square. So, if you first integrate it, you get the velocity. After second integration, we get the position, okay. So, the analytical solution for a 16-dimensional system, 3n position and 3n momenta are simply impossible. This is you cannot do it. So, MD simulation therefore use the finite difference method in numerical step by step fashion. So, instead of what we do that we convert this differential equation into difference equation, okay, and we do the solution in a step by step way. That means we change the times, we change then we change this position within a very minute time, which is called the time step, okay. So, essentially we use the finite difference method in numerical step by step fashion, and we replace the differentials dr dt with finite difference like delta r delta t, and thus transform the differential equation into finite difference equation. For example, this position at a later time t plus delta t is projected forward from the position at time t in a Taylor expansion. So, we can use the Taylor expansion. Let's say we know RT, but we want to get the position at t plus delta t. So, we can use this the Taylor series expansion. So, the first term is nothing but dr dt, second term half of the del 2r del t square, which is nothing but the acceleration, okay. And we can use the higher order terms also, but most of the cases in practical MD run up to third order terms are considered, and higher order terms becomes truncation error expressed as the order. So, most of the cases if we use 3 order terms, essentially the error term will be in the range of t to the delta t to the power of 4, okay. So, now we can manipulate this Taylor series expansion in different way, and we get different algorithm, okay, because let us say what we start with in a molecular dynamic simulation, that means at time t equal to 0, what is the position. So, this position generally we can get from the structural data, from let us say XRD data and all, or we can just use a kind of a random distribution of the atoms, okay. Then we need to get how with times under the influence of different external parameter like temperature, pressure, okay, then how the position changes, okay. So, this position change essentially we need to use different algorithm or different variation or different manipulation of this the Taylor series expansion to get the property to get their position at later time, at the same time also which is kind of the efficient way. So, that means which do not diverge at all, at the same time also which is which require less step to do the energy minimum or potential energy minimization, okay. So, based on this, well, I will discuss mainly 3 main types of this algorithm used. One of them is called the Verlet algorithm. So, in the Verlet algorithm, what essentially we can take, let us say we take the Taylor expansion for forward and backward position. So, this is the forward position, that means if you know delta the position at t, then we want to get it delta t, or if you have, let us say also you know the backward step also, let us say at t minus delta t. So, both these case we can write it as a Taylor series expansion. Now, if we add these two, so essentially we get the position at t plus delta t equals to 2RT minus r at the backward position plus the acceleration into delta t square. So, this acceleration we know it from the potential, okay, and if you know the position at time t and t minus delta t, so we can get the position at t plus delta t. So, that is essentially the Verlet algorithm, okay. So, in this case it requires only 1/4 revolution per delta t, because A is get it from the force evaluation. So, 1/4, but in this case essentially the error will be in the range. Now, if we add it up, so this delta tq term is cancelling out. So, the error will be in the range of in the order of delta t to the power 4. Okay. The first time step need the position at the first time steps need the position at one step backward. So, essentially now you have started 0, but you do not get the minus the position at minus any minus time, okay, backward time. So, what we do? So for just when you start it, so the first step essentially we can manipulate it in other way. So in that case, we essentially we do the Tell expression like this: r at t, there is r at delta t. So essentially t0, let's say t equal to 0. So in that case only you use this. Okay, so rt plus delta t equal to rt plus vt delta t plus at by 2 delta t square. Okay. Of course, in this case, let's say when you start it, so first step we do it like this. From the second step, we can use this this expression. Okay. But at the same time, let's say in this step, essentially you don't have. So this is the main algorithm which you use in the Verlet algorithm case. But in this case, there is no expression for velocity, which is good. But at the same time, also you need to have the velocity to calculate the kinetic energy, or this velocity also relates somewhere with temperature and pressure also. Okay. So after the we use the final equation for the second time step, t plus delta t. Velocity which is required to compute the kinetic energy do not appear in the time evolution by the Verlet algorithm. So there we can calculate it from again using some of the difference equation, like velocity. You can write it the velocity at position at time t plus delta t minus position at t minus delta t divided by 2 delta. So these are the different differential what to say, the approximation of differential equation to difference equation. Okay. So we need to use this another extra step to calculate the velocity if we use the Verlet algorithm. Okay. So this is kind of the two calculation we need to do. So in order to avoid this, another modification is called the velocity Verlet algorithm. Okay. So the velocity Verlet algorithm, which is most frequently implemented methods in molecular dynamics, where the position, velocities and acceleration at time t plus delta t are obtained from the corresponding quantity at time t by advancing t by half step. So essentially we are getting the velocity at half step advance, t plus delta t by 2. Again also we are taking the first two term vt plus half at into delta t. At the same time also r we are advancing a one full step, not half steps. Essentially r t plus delta t. Again we are taking the three terms. Okay. So we are getting rt vt delta t plus half at delta t square. Now this vt plus this term is nothing but v at t plus delta t. So that's what we are writing here. At the same time also, but here we are just directly calculating the acceleration from the potential. Okay. So we are taking the differential of this the potential with respect to the position and dividing by the mass, we get this the acceleration. Okay. So you get the acceleration from here. Okay. So now, but what we are getting here is the velocity at half step advance. Okay. So now what you get, that the advance of, then we need to advance this velocity by full step. So from a at the previous and current time step and express it using the half step advance velocity and the full step advance a. So essentially now b at full step we are using the velocity at the current step plus we are using the acceleration at the current step and the next step. So this next step acceleration we are getting from the force, and we are using this. Okay. So essentially this velocity at the next full step, essentially velocity half step plus the half of the acceleration at the next step. Okay. So in this case velocity is updated only after the new position and acceleration equivalent to new forces are computed. Okay. So this is the most used method for numerical solution of the Newtonian equation of motion.